Hey, so today what we're going to be talking about is the limit of a function. So before we start talking about it, one of the questions a lot of people have is why? Like, why do we have to have this weird mathematical thing? So what we use limits for is when we're talking about something, sometimes you can't just plug the number in. You're going to run into some issues, but what you want to do is you want to see what happens when you get as close to possible. So for example, what we were talking about in the last section, 2.1, was the secant and tangent line, and we had to use this formula, which was f of b minus f of a divided by b minus a. Now, what we wanted to do is that we wanted to use this as b got closer to a. So here was what that looks like, is let's say that we have this point right here, okay, and let's say that this is our point a and f of a. Okay, so this is a. And let's say that we have another point b right here. Okay, so this would be the point b, f of b. So what we want is, instead of having that secant line, what we want is that we want to have the actual tangent line. Okay, so that line, the tangent line, remember, it only goes through at one point. So what that means is that we're going to get closer and closer and closer by getting b as close to a as we can, so that we can find a line that's really, really close to that tangent line. Now, doing that with pictures and also doing that numerically, aka making a table, is great, but it's also time consuming, and sometimes it's not as lucrative as we'd want it to be. And we can't just have b equal a. Now, why can't we just have b equal a? Well, if we do, then we'll have f of a minus f of a divided by a minus a, and that's bad news bears, because if we know anything about math, we know that we are never, ever, ever supposed to divide by 0. So limits are going to help us get a workaround. So now that I've told you why limits are such a lucrative business, let me tell you what a limit actually is. So if we're looking at the limit of a function called f of x, okay, what the limit's going to be is it's going to be the value that f of x gets really close to as x approaches, but doesn't actually have to equal a value a. Now the way we denote that is we say the limit of our function as x gets closer to a equals some value L. Okay, so first what we're going to do is that we're going to explore limits graphically. That means using a picture. So if we look at this first example, we have a graph of the function x squared, so we have this beautiful parabola, and we want to determine the limits. So what we want to know is we want to know what is happening to our y value, or f of x value, as x gets closer to 2. So as our x values get really close to 2, what we want to do is that we want to hit on the graph and see what does it look like our y values are getting closer to. So if we look at values around 2 for our x values, what does it look like our y values are getting close to? Well, it looks like our y values are getting close to 4. So we would say the limit, or the value that our function is approaching, as x gets really close to 2, is going to be 4. Now, if we look at the limit of our function as x approaches -1, so let's see, -1 is right here. If we get closer and closer to -1, what does it look like our y value is getting closer to? So as we get closer to -1, our y value looks like it's getting closer to +1. Awesome. Now, if we look at this graph below, and we do the same thing where we explore this graphically, okay, we want to explore the function f of x equals x cubed minus 2x squared divided by x minus 2. Now, if you look at this graph, something I would like to point out to you guys and highlight is this almost looks identical to the graph that we have above, except that we actually have a hole at x equals 2. The reason we have a hole at x equals 2 is because if you try to plug 2 in for x, you'll end up dividing by 0, which, remember, you are not allowed to do. Not now, not never. So what that means is that our function isn't actually defined at x equals 2. That means we have an empty space. However, remember, our function doesn't actually have to exist there. It just needs to get very, very close. So if we look at this function and this graph, if I get really close to 2, okay, boop, boop, there we go. If I start to get really close to 2, and again, I don't actually have to plug 2 in, I just have to look around 2 and see what does my function look like it's getting close to. It still looks like whether I'm approaching from one side or the other side of 2, remember we have to go all the way up to the graph and then follow it to the y-axis, it still looks like it's going to get really close to 4. So even though it doesn't actually equal 4 because we have an open hole, it's getting really close to 4. Same thing here if we look at x equals -1. Okay, now because that's a solid line, it means it is defined there, so we actually do have the point -1, 1. As we approach from both sides, okay, it looks like it's approaching 1. Now here's the difference between limit values and function values. The limit is what happens as you get infinitely closer but don't actually hit 2. Okay? So as we get infinitely closer but don't actually plug 2 into our function, it's getting closer to 4. But what happens if you actually plug f of 2 into your function? What do you get? Well, you get does not exist, because if you plug in 2, you are going to get 0 over 0, and remember you're not allowed to divide by 0. Alright, let's look at one more example. So what this is this is a piecewise function. So for this piecewise function, it says, hey, as long as x does not equal 2, our graph is going to look like this equation here. So that's why it looks identical to the graph above. However, what it did is it says, hey, if you really want to plug 2 into your function, just have your y value equal 1. That's where this point comes into play. So again, let's look at the limit as x gets really close to 2, but remember, we're not actually going to plug 2 in. So we're getting really close to 2, and if I follow my x value up, remember, all the way to my graph, and follow it over, again, no matter which side I'm getting close to, okay, it still looks like my y value is getting closer to 4. Now again, if I take the limit of -1, okay, it's going to get closer to 1. But here's the thing. What happens if I actually plug x equals 2 into my function? Well, if I plug x equals 2 into my function, what I'm going to get out is I'm going to get out a y value of 1. The reason I'm showing this to you is because our limit doesn't necessarily have to equal our value. Okay? Well, you can kind of think of this as, and I know it sounds a little bit silly, but you can kind of think of it as like a wormhole in space and time where it's like, oh yeah, you look like you're approaching a 7-Eleven, but then when you open the door, all of a sudden you're transported to, I don't know, a Burger King or something. I don't know why we're eating junk food in this example, but we are. So, there's a difference between a limit value and a function value. Now the other thing is that sometimes we only look at limits from one side or the other. So right here we've been looking at it as it comes from the left side, and we've been looking at it as it comes from the right side. So to denote that we're looking at only looking at it from a specific side, what we have is we have two different kinds of limits. We have something called a right-hand limit, and that's when we look at the value our function takes on as our x approaches from the right-hand side. Okay? So what that means is that we're taking x values that are greater than x, and to denote that those values are a little bit greater than x, or a, we put a little plus sign there. Now if we're approaching from the left-hand side, okay, then we're plugging x values from the left. That means that we're taking values that are less than x. And to denote that, we put a little negative in the exponent. Before we get any further, something really important that's going to be kind of a reoccurring theme in this section is that we say that a limit overall just of x approaching a exists if and only if the left-hand side and the right-hand side are equal. Then the limit exists. Okay? Conversely, what that means is that if the left-hand side and the right-hand side don't agree, then your limit does not exist. Okay, and we'll look at some examples of that. So let's go ahead and look at this following example here. So we have this really weird piecewise function, and we're going to explore limits from the left and from the right. So on the first one, we're going to be looking as x approaches -2, but we're only going to be looking as we approach from the left-hand side. So here's x equals -2, and we're going to be looking as we approach from the left-hand side. So as we approach from the left-hand side, what I'm noticing about my y values is that they are getting really small. So they're going down, and they're going down really quick. So it looks like they're going to -infinity. Now, for the other one, if I look at the limit as I approach -2, but now I'm coming from the right-hand side, so now I'm coming from this side, if I look at my y values, what I'm noticing is that the closer I get to -2, the bigger my y values are becoming, and it looks like they're getting big really fast. And this arrow means that it's going to go up forever. So that means it's approaching +infinity. Okay, awesome. Let's do a couple more of these. So let's do the limit as x approaches, let's see, 1 from the left-hand side. So if I approach 1 from the left-hand side, remember I'm following the line on the graph, it looks like it's approaching 1. Now if I approach the limit from the right-hand side, it also looks like it is approaching 1. Now if I asked you, hey, what's the overall limit as x approaches 1? Well, since the left-hand side is approaching 1 and the right-hand side is also approaching 1, I would say that that is 1. Now what happens if I actually plug 1 into my function? Well, if I actually plug 1 into my function, you notice I have this empty hole above, and then I have this filled hole below. The filled hole is what I actually get out if I plug in 1. So if I plug x equals 1 into my function, I'm going to get out -1. Alright, go ahead and pause the video and try some of these on your own, and then unpause it and check and see if you did pretty good. Alright, so let's look at H, K, C, F, I, and L together, because that's definitely how the alphabet goes. So if we look at as x approaches 2 from the left, okay, remember we're going to follow this down to our graph and see what does it look like my y values are getting closer to. So as I get closer to x equals 2, it looks like my y values are getting closer to -2. For the next one, as I approach from the right-hand side and find the graph and follow it, it looks like those y values are getting closer to +1. Now, when it asks, what's the overall limit as x approaches 2? Well, that's kind of like asking, hey, if you're getting closer to 2, what's your final destination? And I have two opposing ones. Well, if I come from the left-hand side, it looks like the destination is -2. If I come from the right-hand side, it looks like the destination is 1. So remember, if they don't equal, or if the graph is split there, we say that the limit does not exist. All right, very last one. The limit as x approaches 3 from the right. So if we approach 3 from the right-hand side, if I go up and over, what's happening, remember that arrow pointing up means it's going to go up forever. That means it's approaching infinity. If I look at it from the left-hand side, okay, it looks like my y values are getting closer to 0. So again, what is the actual limit if I just asked you what's the limit as x approaches 3? Well, since one side is approaching 0 and the other side is approaching infinity, it would not exist. All right, last but not least, this one's actually really important. What is the limit of our function f of x as x approaches 4? So let's do this in two parts. Let's approach it from the left-hand side. So as I approach from the left-hand side, it looks like it's approaching 0. So we'll say the limit as x approaches 4 from the left-hand side equals 0. Now, what is it when I approach from the right-hand side? Well, if I approach from the right-hand side, what I see happening is I don't have a graph. So if I don't have a graph, that means that it's undefined or does not exist. So the limit as I approach x equals 4 for my function f of x, well, since I don't have one of the sides, I don't have the right-hand side, that would also be dne, because there's nothing over here, right? It's just a big empty space. All right, now I'm going to go ahead and pause this video and make a second video for exploring limits numerically.